The universe you know might be an illusion. Its smooth, continuous fabric of space and time could be woven from countless invisible quantum threads. This is the profound mystery of how reality is built. Physicist John Wheeler once described space-time as foamy at the smallest scales, a concept that shatters our everyday perception. By the end of this journey, you will understand how this radical idea could unite the laws of physics. We will uncover how the bizarre rules of the quantum world might stitch together the cosmos itself, revealing what happens at the heart of a black hole and what existed before the Big Bang. What does it mean for our reality if the stage itself is not fundamental? That deep conflict between two pillars of physics left the universe looking strangely divided. One set of rules, Einstein's grand vision of warped space and time, masterfully governed the cosmos. The other, the quantum rules of chance and uncertainty, dictated the frantic dance of the tiny particles that make up everything. For a long time, this was simply how things were. You could use one rulebook for stars and galaxies, and the other for atoms and electrons, but this separation could not last. The universe is one entity, after all. There had to be a single, deeper set of laws, a unified theory waiting to be found. The first major attempt to build a bridge came from an idea so radical it proposed that the fundamental ingredients of reality were not particles but tiny, vibrating strings. Imagine the universe is not made of dots but of inconceivably small loops. The different vibrations of these loops, like the strings on a cello playing different notes, would produce every particle and force we see. A certain vibration might be an electron, another a photon of light. This was string theory, and it was breathtakingly elegant. It promised to weave gravity into the quantum world, finally uniting the cosmos. Yet this beautiful idea came with a profound and puzzling cost. For the math of these vibrating strings to work, our familiar universe of 3 dimensions of space and 1 of time was not enough. The equations demanded more. They required extra, hidden dimensions of space, curled up into shapes so tiny we could never perceive them. The very fabric of our reality, it seemed, was far more spacious and intricate than we ever dreamed. That smooth pond, a perfect vacuum, is not so empty after all. Beneath its apparent calm, the void is alive with a faint, ceaseless fizz. These are not ripples from a thrown stone, but spontaneous, fleeting disturbances. This is the revolutionary picture painted by quantum field theory. It proposes that the entire universe is filled with invisible, fluid-like entities known as fields. An electron is not just a solitary point, but a tiny knot of energy, a ripple in the universal electron field. A particle of light is a vibration in the photon field. Every fundamental particle we know is merely an excitation of its own unique, underlying field, a note played on a cosmic instrument. This profound shift in perspective was the first great leap toward unifying physics. It allowed minds like Paul Dirac and Richard Feynman to weave quantum mechanics seamlessly with Einstein's special relativity. Feynman gave us a powerful visual language, his famous diagrams, which turned the incredibly complex mathematics of particles colliding and transforming into elegant, almost cartoon-like pictures. With this new toolkit, physicists could describe 3 of nature's 4 fundamental forces with stunning accuracy: the electromagnetic force, which holds atoms together, and the strong and weak nuclear forces, which govern the atom's heart, all bowed to the rules of quantum field theory. But one force remained stubbornly outside this beautiful framework: gravity, the force that sculpts galaxies and bends the path of light, simply did not fit. It was the one guest who refused to join the quantum party, leaving physicists with a glaring, fundamental question. If fields and quanta describe everything else, what strange music does gravity play? Gravity is the quietest force in the universe. Its profound weakness becomes its ultimate defense against our understanding. While the other fundamental forces shout their presence in the frantic quantum realm, gravity only whispers, its faint voice lost in the cacophony. This is the heart of the Great Divide. Think of a calm, rolling hillside, its smooth curves defining the landscape. This is the world of general relativity, where space and time are a single, malleable fabric. Now try to build that same smooth hillside using only individual, separate grains of sand. Each grain is a quantum, a tiny, discrete packet of energy. This is the impossible task physicists face. The mathematics that so perfectly describes the smooth, continuous fabric of space-time completely breaks down when forced to describe it in discrete quantum chunks. The equations predict infinite energies and impossible probabilities, clear mathematical screams that our approach is fundamentally wrong. For decades, this impasse has stood as a towering wall in theoretical physics. We have a flawless theory for the very large and a brilliant theory for the very small, but they speak different, mutually exclusive languages. This failure to quantize gravity is not a minor puzzle. It is a glaring sign that we are missing something deep, something that forces us to reconsider the very nature of reality itself. The search for a solution is pushing us to ask a question so basic we rarely think to ask it. What if space and time are not the stage upon which the universe plays out, but are themselves part of the performance? This idea turns our entire understanding of the cosmos inside out. What if the space you move through and the time you experience are not the bedrock of reality, but are instead like a grand performance emerging from a hidden ensemble of actors? This is not a small adjustment. It is a complete paradigm shift, suggesting that the smooth, continuous fabric of the cosmos is a collective illusion. Think of the temperature of the air in a room. You feel it as a single, definite quality, warm or cool, but this sensation does not come from a fundamental substance called temperature. It emerges from the frantic, chaotic motion of countless invisible molecules. The smooth experience is a large-scale approximation of a hidden, discrete reality. In the same way, the seamless stage of space and time might be a similar emergent phenomenon. It is the macroscopic result of an unimaginable number of underlying quantum events, a pattern that only becomes smooth when you zoom out. Philosophers and physicists like Carlo Rovelli have championed this radical perspective, proposing that reality at its most fundamental level could be a vast network of relations. In this view, things are defined not by where they are in some pre-existing space, but purely by how they interact with each other. It is a universe of connections without a container. This concept demands we abandon our deepest intuitions about location and distance, but it offers a breathtakingly promising path forward. It dissolves the central conflict between the smooth fabric of gravity and the chunky nature of the quantum. If space-time is not fundamental, then we no longer need to force gravity into a quantum box. Instead, we can ask what deeper reality gives rise to both. And the answer to that profound question may lie in one of the most mysterious and powerful phenomena in all of physics, the strange, invisible link known as quantum entanglement. Einstein famously dismissed it as spooky action at a distance, a ghostly link that seemed to violate the very speed limit of the universe. Picture two coins, each flipped in a different galaxy, yet somehow always landing on the same side at the exact same moment. This is the essence of quantum entanglement. When two particles become entangled, their fates are irrevocably linked. Measure the spin of one particle here, and you instantly know the spin of its partner, no matter if it is across the room or across the cosmos. For generations, this phenomenon was viewed as a profound but isolated oddity, a strange quirk of the quantum world with no bearing on the large-scale structure of reality. It was a fascinating puzzle, but just a puzzle. That perspective has now been completely overturned. A revolutionary new idea suggests that entanglement is not just a curiosity. It might be the fundamental thread weaving the very fabric of space and time. Think about what makes space feel like space. It is the ability to be here and for something else to be there, and for there to be a connection between you. This connectivity, this geometry of near and far, may emerge from an unimaginably complex web of quantum entanglements. Each entangled link creates a tiny bridge of correlation, and the collective pattern of countless trillions of these bridges could generate the smooth, continuous landscape we move through. Entanglement is no longer just a feature within space-time. It is now a prime suspect for what creates space-time itself. This transforms our understanding from a universe where things are connected through space to a universe where space itself is the connection. How can a ghostly link between particles create the solid ground beneath your feet? The answer may lie in the geometry of connection. Think of a vast, intricate spiderweb. Each individual silk thread is nearly invisible, but the pattern of connections they form creates a definite, tangible structure that holds its shape in the air. In a very similar way, the complex web of quantum entanglement between countless microscopic building blocks could be what generates the geometry of space-time itself. This is not just a poetic analogy. It is formalized in a profound idea known as the ER equals EPR conjecture. This proposal creates a stunning bridge between two of Einstein's most famous concepts. On one side is EPR, named for the paper on entanglement he co-authored, representing that spooky correlation. On the other is ER for Einstein-Rosen bridges, which we commonly call wormholes. The conjecture suggests these are two sides of the same coin. Two entangled particles are not just mysteriously linked. They are connected by a microscopic, non-traversable wormhole, a tiny bridge in the geometry of space. This provides a breathtakingly concrete vision. The space we move through is not a passive stage. It is actively woven from a dense, dynamic network of quantum correlations. Every entangled link is a single thread, and the collective tapestry is the reality we experience. To understand how this weaving process actually works, we must look at the specific theoretical frameworks that make this radical idea explicit. A cosmic DVD holds all the information for a movie, encoding a rich, three-dimensional world onto its flat, two-dimensional surface. This is not just a metaphor. It is the startling premise of the holographic principle, which suggests that our entire universe, with all its depth and dimension, might be a grand projection from a distant, two-dimensional boundary. This idea first emerged not from pure speculation, but from the deep puzzles of black holes. Physicists discovered that a black hole's entropy, which is fundamentally a measure of its hidden information, is not proportional to the volume of its dark interior, but to the surface area of its event horizon. It is as if all the information about what fell into the black hole is not lost inside, but is smeared like a perfect microscopic film across its surface. This single, bizarre fact hints that the universe might be fundamentally lower dimensional, and that the three-dimensional reality we move through is an emergent holographic illusion. The profound implication is a cosmic redundancy. We may not need the full three dimensions to describe everything in the cosmos. The true, fundamental description of reality could be happening on a distant, flat surface, and our world of depth and distance is a magnificent projection from that boundary. This principle provides a powerful mathematical language for understanding how information and geometry are inextricably linked. It transforms the fabric of space-time from a given stage into a dynamic, encoded image, a construct that emerges from the information stored at its edges. This framework finds its most concrete and successful realization in a specific, mind-bending correspondence that has revolutionized our approach to quantum gravity. A perfect dictionary for the cosmos was discovered in 1997. It did not translate between human languages, but between two entirely different descriptions of reality. This is the anti-de Sitter conformal field theory correspondence, a mathematical Rosetta Stone proposed by physicist Juan Maldacena. It gives us the first complete and precise example of the holographic principle in action. The correspondence creates a stunning duality. It states that a theory of gravity operating inside a special kind of hypothetical space, one with a negative curvature, is mathematically identical to a quantum field theory that lives only on the flat boundary of that space. One is a world with gravity and depth, the other is a world without gravity, existing on a lower dimensional edge, and they are two different descriptions of the exact same physical situation. This is far more than a curious analogy. It is a full mathematical equivalence, a dictionary that allows physicists to translate an impossibly difficult problem in quantum gravity into a more manageable problem in a well-understood quantum theory. A question about how black holes behave in the bulk of that space becomes a question about the thermal properties of its quantum boundary. It is as if you could understand every intricate detail of a sculpture, not by studying the statue itself, but by perfectly decoding the two-dimensional shadow it casts on a wall. This correspondence provides our most powerful testing ground for how the threads of quantum information can weave the classical fabric of space. While our own universe is not a perfect match for this specific hypothetical space, the insights are profound and inescapable. It strongly suggests that our experience of a gravitational, three-dimensional world is a magnificent and useful illusion, a holographic projection from a quantum source we are only beginning to comprehend. This concrete duality forces us to confront a truly radical possibility, that the fundamental laws of the universe may be written in a language that does not include space or time at all. From a bird's eye view, a city's complex dance of traffic and light reveals a profound truth. No central director choreographs this flow. It emerges organically and beautifully from the countless independent decisions of millions of people. In a strikingly similar way, the very fabric of the cosmos might operate. The theory of emergent gravity proposes that space-time and the force we call gravity are not the foundational layers of reality. They are not the stage itself. Instead, they are the collective result, the large-scale pattern that arises from the interactions of countless microscopic constituents. Physicist Eric Verland has championed this radical view, suggesting gravity is not a fundamental force at all, but what we call an entropic force. Think of the natural tendency of the universe to move towards disorder. A drop of ink spreads through water, not because of a fundamental attraction, but because there are vastly more ways for the ink molecules to be spread out than to be clustered together. The system evolves toward that state of higher entropy, which is a measure of this disorder. In Verland's framework, gravity is a manifestation of this same statistical tendency. The attraction you feel, the reason an apple falls, is not a fundamental pull. It is a collective push. It is the universe's tendency to increase entropy, driven by the rearrangement of the most basic bits of information that constitute reality. This perspective does not just tweak our understanding of gravity. It completely demotes it, transforming it from a primary force into a secondary, emergent phenomenon, deeply rooted in the laws of thermodynamics and the physics of information. This breathtaking shift in perspective forces one of the most fundamental questions in all of physics. If gravity and space-time are collective illusions, what is the true nature of the individual actors on this cosmic stage? What are these fundamental bits of information whose collective behavior weaves the world we see? While string theory weaves extra dimensions into its fabric, another profound framework asks us to look closer at the stage itself. What if space-time is not smooth but pixelated? Loop quantum gravity proposes that the cosmos is not a continuous sheet, but a tapestry of finite, indivisible threads. The gravitational field, the very essence of space, is not a fluid backdrop. It is composed of tiny, one-dimensional loops of excited field, each a fundamental stitch in reality's quilt. Imagine the finest silk mesh, its strength and texture arising entirely from the interweaving of individual threads. In this view, space is not infinitely divisible. It comes in the smallest possible packets of area and volume, a cosmic atomism applied to geometry itself. This granularity is captured by beautiful mathematical structures known as spin networks. Picture a vast, evolving web of connections. In this web, the links themselves represent the quantized areas, while the nodes where they meet represent quantized volumes. The entire network is space, frozen in a single moment, but our reality is not static. We experience a flowing, dynamic space-time. This is where the loops of loop quantum gravity come alive. The network evolves, its connections changing and rewriting themselves in a cosmic dance. The smooth, curved geometry of general relativity that we observe on the scale of planets and galaxies is not fundamental. It is the average, large-scale behavior of this frantic, discrete choreography, much as the smooth flow of a liquid emerges from the chaotic jostling of its molecules. This approach is powerfully direct. It requires no extra hidden dimensions, seeking instead to apply the rules of quantum mechanics directly to the geometry of space as described by Einstein. It gives us a concrete, if mathematically complex, vision of a universe built from the bottom up, where even the void between stars is a vibrant lattice of quantum connections. This granular picture of space-time inevitably leads us to wonder about the most extreme environments in the universe, places where this fabric is stretched to its absolute limit. These tiny vibrating strings offer a breathtakingly elegant solution to the quantum gravity problem. Their music dictates the very nature of reality. A string vibrating at one precise frequency manifests as an electron, while a different resonant pattern produces a photon. Most profoundly, one unique vibration corresponds to the graviton, the hypothetical particle that would carry the gravitational force. For the first time, gravity is not an awkward outsider but a natural part of the cosmic orchestra, emerging seamlessly from the same fundamental principle as everything else. Yet this beautiful harmony comes at a cost. The mathematics of these vibrating strings only remains consistent if the universe provides them with more room to perform. Our familiar 3 dimensions of space are not enough. The equations demand extra spatial dimensions, often 6 or 7 more, curled up into intricate, microscopic shapes known as Calabi-Yau manifolds. These hidden dimensions are not empty voids but complex geometric forms, their specific topology determining the properties of the particles and forces we observe in our large, expanded dimensions. Every possible vibration, every particle, every law of physics in our universe could be an echo of this hidden, compact geometry. This framework presents a cosmic landscape of staggering possibilities, a vast collection of potential universes, each with its own unique set of physical laws. While this vision is powerful and mathematically rich, it remains, for now, frustratingly beyond the reach of direct experimental proof. This lack of testable predictions has pushed physicists to explore new paths, ingenious frameworks that build upon the lessons of string theory while attempting to chart a more direct course toward observable reality. The geometry of space can be described by a silent, shifting network. This is the vision of spin networks in loop quantum gravity, where reality is a vast, evolving graph. The nodes of this graph represent the tiniest possible volumes of space, while the links connecting them define the areas that separate one volume from its neighbor. There are no points or coordinates in this fundamental picture, only a pure web of relationships. The entire three-dimensional world you perceive, with its distances and directions, emerges from the intricate pattern of this network's connections. It is a combinatorial description of quantum geometry, where space is literally built from the bottom up by discrete, informational links. At the same time, a completely different mathematical landscape was being painted by Roger Penrose. His twistor theory turns our conventional understanding inside out. In this framework, the familiar points of space and time are not the primary ingredients. They are secondary constructions derived from more fundamental objects called twistors. A twistor is fundamentally tied to a ray of light, a null line in space-time. Instead of thinking of a particle moving through space, twistors describe the entire history of that particle's path as a single, holistic object. In this light-first perspective, the geometry of our universe is woven from the fundamental relationships between these twistors, making it exceptionally elegant for describing the scattering of high-energy particles. These alternative landscapes, from spin networks to twistors, reveal a profound truth about the quest for quantum gravity. The path is not singular. It is a sprawling exploration of mathematical beauty, where each framework uncovers a different facet of a potential deeper reality. This vibrant diversity is not a sign of confusion, but a testament to the creative ferment driving physics forward. It forces us to consider that the most fundamental currency of the cosmos might not be energy or matter, but something far more abstract and powerful, the very concept of information itself. John Archibald Wheeler offered a vision of reality so radical it redefines the word fundamental. He proposed that the bedrock of the cosmos is not energy or matter, but information. He called this idea it from bit, suggesting that every particle, every force, and even the fabric of space-time itself ultimately springs from binary responses to simple yes or no questions. At the very bottom, existence is a tapestry woven from bits of information. This transforms the universe from a collection of things into a vast, ongoing computation. The laws of physics we observe are not arbitrary rules, but the deep-seated algorithms this cosmic computer is running. The strongest evidence for this digital physics perspective comes from the most enigmatic objects in the cosmos, black holes. Their entropy, which measures their hidden information content, is not proportional to their volume but to the surface area of their event horizons. This is a direct physical clue that information is not merely contained within the universe, but that the universe itself is fundamentally made of information. The very geometry of space-time, its smooth curves and warps, could be a grand, emergent display of how this underlying information is organized, processed, and entangled. To grasp how this cosmic processing might operate, we must explore the most powerful information processor we know of, the quantum computer, and consider its staggering implications for the nature of reality itself. A classical computer operates with absolute certainty. Its bits are definitive yes or no. Yet the quantum world refuses such simplicity. A qubit, the fundamental unit of a quantum computer, embraces a state of potential. It can be a 0, a 1, or a ghostly combination of both at the same time. This is superposition, and it allows a quantum computer to explore a near-infinite number of possibilities simultaneously, solving problems in a parallel symphony that would take a classical machine eons to compute. Now extend this principle to the cosmos itself. If the fundamental layer of reality is a vast, intricate quantum system, then the universe itself could be seen as the ultimate quantum computer. Its continuous evolution, the unfolding of every event from the birth of a star to the falling of a leaf, might be understood as an unimaginably complex computation. The strange, non-local threads of quantum entanglement that weave the fabric of space could be the very circuitry of this cosmic processor. The smooth geometry of space-time that emerges from this quantum underworld might be the output, the final display of a calculation happening on a scale we can scarcely fathom. This perspective is more than a poetic metaphor. It provides a powerful new dictionary for translating the mysteries of gravity. Physicists have discovered a stunning link between the computational complexity of a quantum state and the geometry of space itself. The complexity here is a measure of how difficult it would be to construct a particular quantum state from a simple starting point. Remarkably, this abstract computational difficulty appears to be dual to a concrete geometric quantity, like the volume of space hidden behind a black hole's event horizon. A more complex quantum state corresponds directly to a larger interior volume in the gravitational description. This means that the hidden realms of our universe, the deepest stretches of space, might be understood not just as empty volume, but as a manifestation of profound computational effort. The universe is not just containing information, it is actively processing it, and the force we call gravity is a shadow of that relentless computation. To truly read the universe's source code, we must move from beautiful theory to tangible proof, seeking the faint echoes of these quantum threads in the reality we can observe and measure. The ultimate challenge is one of scale. How do you observe a universe built from threads a billion times finer than an atom? You cannot see them directly, but you can search for their shadows, for the subtle ways they might disrupt the smooth perfection of classical physics. One of the most promising searches looks to the far reaches of the cosmos, to the most violent explosions we can detect. When a gamma ray burst erupts from a distant galaxy, it sends a torrent of photons racing across the universe. These photons are all born at the same instant, but they travel with different energies. If space-time is a churning quantum foam, it might act like a kind of cosmic surf. Higher energy photons, with their shorter wavelengths, could interact more strongly with the foam's fine grain, slowing them down by a minuscule amount compared to their lower energy counterparts. By the time these photons complete their billion light-year journey to our telescopes, this tiny delay could be amplified into a measurable signal. A split in the arrival time of these cosmic messengers would be a direct whisper from the granular structure of reality itself. Another frontier lies not in the heavens but in laboratories here on Earth. Scientists are creating tabletop universes using clouds of atoms cooled to near absolute zero. At these temperatures, the atoms lose their individual identities and merge into a single quantum state known as a Bose-Einstein condensate. In this exotic material, sound waves behave in ways that are mathematically analogous to light waves moving through a curved space-time. By carefully manipulating these atomic clouds, researchers can effectively simulate the conditions near a black hole or the birth of the universe, watching how information and entanglement flow in these analog systems. These are not direct tests of quantum gravity, but they are profound experiments that test the principles we believe are at work, offering a glimpse into the underlying logic of the cosmos. The most sensitive rulers ever built, the gravitational wave observatories like LIGO and VIRGO, are also joining the hunt. As these detectors become ever more precise, they may begin to pick up a new kind of background noise, a faint hiss that cannot be explained by any conventional source. This could be the collective sound of space-time's fundamental grains jostling at the smallest possible scale, a signature of the universe's pixelated nature imprinted on the ripples of gravity. The quest is monumental, a search for a ripple in an ocean by studying the behavior of its waves. Yet each of these experimental paths represents a bridge, a way to bring the most abstract theories of reality into the tangible realm of observation and evidence. This relentless drive to test our grandest ideas pushes our technology to its absolute limits and forces us to confront the ultimate nature of the stage upon which we exist. A black hole is far more than a cosmic vacuum. It is the ultimate testing ground for the quantum nature of gravity, a place where the universe's two rulebooks are forced into a final, decisive confrontation. At its edge lies the event horizon, a boundary of no return. Cross this invisible threshold, and not even light can escape the gravitational pull. Deeper still lies the singularity, a point where the equations of general relativity scream into infinity, a clear sign that our classical understanding of space and time has completely shattered. It is here, at these extremes, that the quantum threads of reality must reveal their true nature. The first great crack in the classical picture came from Stephen Hawking. He realized that the void of space is not empty near the event horizon. Intense tidal forces of gravity warp the quantum fields, causing pairs of virtual particles to pop into existence. Normally, these particles would annihilate each other instantly, but at the very edge of the black hole, one particle can fall in while the other escapes, stealing a tiny amount of the black hole's energy. This steady stream of escaping particles is Hawking radiation, a faint glow that proves quantum mechanics is at play even in the heart of gravity's domain. This radiation carries a devastating consequence. Over eons, a black hole loses mass, slowly evaporating until it potentially vanishes entirely. This evaporation creates one of the most profound puzzles in all of physics, the black hole information paradox. Quantum mechanics states that information is never truly lost. The specific configuration of every atom that falls into a black hole should, in principle, be preserved, even if scrambled beyond recognition. But if the black hole evaporates into a featureless bath of Hawking radiation, where did that information go? Its permanent loss would mean the foundational laws of quantum theory are wrong. The resolution likely lies in the quantum fabric of space-time itself. The information is not lost inside the crushing singularity. Instead, it may be meticulously encoded on the event horizon itself, a holographic film preserving the history of everything that fell in. Or it could be woven into the intricate web of quantum entanglement that connects the radiation particles to the black hole and to each other. Every particle that escapes is entangled with the black hole's interior, and the information is slowly and chaotically transferred outward through this network. This is why black holes are such powerful guides. Any theory of quantum gravity must solve this paradox. It must explain how information flows, how the threads of entanglement stitch together the event horizon, and how a seamless space-time emerges from this quantum chaos. By studying these darkest of cosmic objects, we are reading the universe's own manual on how reality is woven together. This peaceful descent is a lie. For decades, physicists held two contradictory truths about crossing a black hole's event horizon. General relativity promised you a quiet, uneventful journey, a principle known as no drama. You would feel no sudden jolt, no searing heat as you passed that invisible threshold. Yet a deep look into quantum mechanics reveals a horrifying alternative. To prevent the permanent loss of information, the math suggests the horizon cannot be a placid place. It must be a blazing firewall, an annihilating curtain of unimaginably energetic particles that would instantly vaporize anything approaching it. One theory guarantees a smooth passage, the other a violent end. This is the Firewall Paradox, and it represents a crisis point in our understanding. The two foundational pillars of modern physics make mutually exclusive predictions about the same event. To resolve this, we must surrender our classical image of a sharp, definite boundary. The true event horizon may be a fuzzy, dynamic quantum structure, a region where the very concepts of here and there break down. In this blurred zone, information is not lost but constantly swapped and reprocessed through a dense web of entanglement. The infalling object and the Hawking radiation remain quantum connected in a way that prevents the need for a destructive firewall. This ongoing clash is not a sign of failure, but a powerful engine of discovery. It forces theorists to build a new language, one where information, entanglement, and geometry are inseparable parts of a single, deeper reality. The ultimate test for any theory of quantum gravity lies at the very beginning of everything. General relativity takes us back to a moment of infinite density and temperature, a singularity where the equations of physics simply break down. It is a mathematical warning that our understanding is incomplete, a sign that we need the quantum rules to describe the cosmos in its first fleeting moments. This is not just a technical problem, it is the fundamental question of how something can emerge from what seems like nothing. The concept of a singular beginning, a hard start to reality, is what a quantum perspective seeks to replace. In the framework of loop quantum cosmology, the Big Bang was not a true beginning but a dramatic transition. Imagine the previous phase of the universe not as an empty void, but as a vast, contracting cosmos. As it collapsed under its own gravity, reaching an extreme of density, the repulsive force generated by the quantum geometry of space itself became overwhelming. Instead of crushing down to a point of infinity, the universe rebounded. This is the Big Bounce, a cosmic renewal where a prior era of contraction gave way to our current expanding universe. The smooth fabric of space-time we see today is the legacy of that quantum-driven event. But how can we possibly find evidence for such a primordial event? The clues are written across the entire sky, in the faint afterglow of the Big Bang itself. The cosmic microwave background radiation is a fossil light from when the universe was just 380,000 years old. This radiation is not perfectly uniform. It contains tiny variations in temperature, a speckled pattern of slightly hotter and colder spots. These primordial fluctuations are the seeds from which all cosmic structure grew, the gravitational blueprints for galaxies and clusters of galaxies. And these fluctuations are thought to be quantum in origin. In the first instance after the bounce, the fabric of space-time would have been a turbulent quantum foam. The same mechanism that drives Hawking radiation from black holes is believed to have operated on a cosmic scale, magnifying tiny quantum jitters in the gravitational field into the classical density variations we see imprinted on the cosmic microwave background. By mapping this ancient light with incredible precision, observatories are effectively looking back to a time before the first stars or galaxies existed. They are reading the faint echoes of the universe's quantum birth, searching for a specific signature in the polarization of this light that could only be caused by gravitational waves from that initial inflationary burst. Finding that signal would be like discovering the first woven threads in the cosmic tapestry, direct evidence that the largest structures we see today were spun from the smallest quantum vibrations at the dawn of time. Our daily reality is defined by the relentless march of time, yet this most fundamental experience becomes a profound mystery when we turn to the universe's rulebooks. In Einstein's theory, time is not a separate, universal clock. It is a dynamic dimension woven into the fabric of space-time, capable of stretching and warping. Your time and my time can tick at different rates depending on our motion and gravity. Meanwhile, the equations of quantum mechanics treat time as an absolute external background. It is the rigid stage on which the quantum dance unfolds, never affected by the dancers. This is the problem of time, a deep schism that prevents the two great theories from uniting. How can you merge a dynamic, pliable time with a static, absolute one? The conflict is so severe that in some approaches to quantum gravity, time vanishes from the fundamental equations entirely. The Wheeler-DeWitt equation, a pioneering attempt to quantize gravity, describes a static universe. In this timeless picture, nothing ever happens. There is no before or after, only a single, frozen quantum state of the entire cosmos. This is a shocking conclusion, but it points toward a radical possibility. The flow of time, with its clear distinction between past, present, and future, may not be a fundamental feature of reality. It could be an emergent property, a collective illusion that arises from the universe's immense complexity and our own interaction with it. Think of a single, unmoving frame from a film reel. The entire story is there, encoded in that one image. The experience of a flowing narrative only emerges when the film is projected, when the frames are sequenced by the projector's light. In a similar way, our conscious experience may be the projector that creates the sensation of a moving present from a timeless underlying reality. This illusion is powered by quantum processes. The definite past we remember and the definite present we experience emerge from a fog of quantum possibilities through a process called decoherence. As quantum systems interact with their environment, their superpositions collapse and their quantum correlations become classical, stable records. Our perception of time's arrow, its one-way direction, may be a consequence of the increasing entanglement of everything in the universe. We are not separate observers watching time pass. We are participants inextricably linked to this ever-growing web of quantum connections, and from our perspective within the web, we perceive its constant rewiring as the unstoppable flow of time. This forces us to confront a staggering idea. The river of time you feel carrying you forward might be the current of quantum information itself, and your consciousness is the vessel riding its waves. Perhaps the most minimalist vision of all strips away geometry entirely. What if the smooth, continuous stage of space-time is not just an approximation of tiny loops or vibrating strings, but an illusion spun from something even more basic, a cosmic list of events? This is the radical proposition of causal set theory. Its fundamental ingredient is not a particle or a field, but a simple relationship, cause and effect. Imagine the entire history of the universe, every single event from the decay of an atom to the birth of a star, written down as individual points. Now, draw a line from one point to another if the first event can influence the second. A flash of lightning here must be connected to the clap of thunder that follows. The firing of a neuron is linked to the thought it produces. This vast, growing web of causal connections is called a causal set. It is the universe reduced to its most essential skeleton, a pure network of before and after. In this view, the space between events is not fundamental. The distance from here to there, the volume of a room, the very geometry we take for granted, is not written into the code of reality. Instead, it emerges. The smooth, four-dimensional continuum of space-time is a secondary, approximate picture that our brains construct from the dense, discrete pattern of these causal links. The theory's power lies in its stark simplicity. It requires only two things: a set of discrete points and an order that defines what causes what. From this sparse beginning, the richness of our world is meant to arise. This approach naturally incorporates a fundamental graininess to the universe, preventing the infinities that plague other theories, and it offers a profound explanation for time's arrow. The feeling that time only moves forward is not a law of physics, but a property of this ever-growing network. As new events are added to the causal set, the web of causality expands, and we, living within that web, perceive this growth as the relentless flow of time. It is a universe where connection is everything, and the stage itself is merely a shadow cast by the timeless logic of cause and effect. The very concept of a location dissolves under this intense scrutiny. We are accustomed to a world where a point on a map is a definite thing, a precise here distinct from every other there. Yet at the universe's most fundamental level, this certainty may be an illusion, a casualty of a strange new geometry. In the framework of non-commutative geometry, developed by mathematician Elaine Connes, the stage of space-time becomes inherently fuzzy. Think of trying to measure the exact position of an object. In our everyday world, it does not matter if you measure its distance north to south first or east to west first. The order of your measurements is irrelevant because the coordinates commute. They yield the same result regardless of sequence, but in this radical view, the coordinates of space-time cease to commute. Measuring position in one direction and then another could give a subtly different result than if you reversed the order. The act of observation itself disrupts the very geometry you are trying to measure. This is not just a mathematical curiosity. It is a direct and profound echo of the quantum uncertainty we find in the particle world, but now applied to the fabric of space itself. It is as if the uncertainty principle has infected the stage, not just the actors. In this algebraic description of reality, precise points lose all meaning. Geometry is no longer about distances and shapes in a classical sense, but is defined by the relationships between abstract mathematical operations. The smooth, continuous space of our intuition is replaced by a frothy, non-commutative foam where the ideas of here and there are only ever approximate. This is not a flaw in our measurements, but a fundamental feature of the cosmos, another powerful signal that the solid ground of reality we perceive is a grand and seamless illusion emerging from a realm that defies all our classical expectations. The mathematics of particle collisions has always been a story of overwhelming complexity. To predict the outcome of even the simplest scattering event, physicists had to laboriously add up thousands upon thousands of Feynman diagrams, each one a picture of a different possible path the particles could take. It was a calculation of breathtaking intricacy, a sprawling forest of possibilities that obscured the simple shape of the final answer. Then a new form was discovered, a geometric object of sublime beauty called the Amplituhedron. This shape exists in a realm of many dimensions, a pristine mathematical landscape where the probabilities of particle interactions are not computed through endless sums, but are simply read off as the volume of the shape itself. The most profound aspect of this discovery is what it leaves out. The Amplituhedron's geometry calculates the outcomes of particle collisions without any reference to space-time. It has no concept of here or there, of before or after. It does not use the principle of locality, the foundational idea that objects can only be influenced by their immediate neighbors. This geometric object produces the correct answers for particle behavior while operating in a realm more primitive than space and time. It is as if we have been trying to understand a sculpture by studying every single shadow it casts from every possible angle, and then someone handed us the sculpture itself. The Amplituhedron suggests that the space-time we inhabit, with its definite locations and causal chains, is not the fundamental stage. It might be a secondary, emergent property, a shadow projection from a deeper, more elegant geometric reality where concepts like distance and separation simply do not apply. This points toward a future physics where space-time is not the starting assumption but the final, beautiful result. This accelerating expansion is the universe's greatest unsolved riddle. The force driving it, dark energy, represents a staggering gap in our understanding, one that quantum gravity must eventually fill. Einstein himself introduced the idea of a cosmological constant, a kind of innate energy woven into the fabric of space itself, which could either attract or repel. He later discarded it as his greatest blunder, but modern observations of distant supernova have proven it to be a prophetic insight. The cosmos is not just expanding, it is flying apart faster and faster, as if space itself possesses a latent, repulsive energy. When theorists try to calculate the strength of this energy from first principles, the result is a number of such monumental wrongness it defies comprehension. The predicted value is 1 followed by 120 zeros too large. If this calculation were correct, the universe would have been torn apart before the first stars ever had a chance to form. The fact that we exist at all is a testament to a miraculous near-cancellation, a delicate balance that hints at a deeper mechanism at work. This is the cosmological constant problem, and it points directly to the quantum vacuum. That seething sea of virtual particles, the quantum foam we discussed earlier, must possess an immense intrinsic energy. According to general relativity, all energy gravitates, so this vacuum energy should curve space-time violently. Yet we observe a universe that is remarkably flat on large scales. Why does the frantic activity of the quantum world weigh so little? A theory of quantum threads must explain this incredible suppression. Perhaps the web of entanglement that weaves space-time also acts to stabilize it, providing a structural rigidity that prevents the vacuum energy from dominating the cosmos. The very same quantum connections that build the stage may also be fine-tuning its expansion, setting the value of dark energy through the collective behavior of countless microscopic threads. This suggests that the fate of the entire universe, its ultimate expansion into cold emptiness or some other destiny, is not determined by a single number in an equation, but by the emergent, self-regulating properties of the quantum fabric from which everything is spun. The newborn universe was a seething, featureless blaze where every piece of reality was directly linked to every other. In this primordial state, the very idea of distance was meaningless, for there was no far or near, only a totality of immediate connection. This is the startling starting point of quantum gravity, a theory that envisions space not as a static stage, but as a dynamic, evolving network. Think of it as a cosmic social web in its earliest, most chaotic phase. In the beginning, every single node, every fundamental constituent of reality, was friends with everyone else. There was no structure, only a hot, undifferentiated tangle of pure relation. Then the universe expanded and cooled, like a supersaturated solution suddenly crystallizing. This hyper-connected network underwent a phase transition. Vast numbers of links were severed. The all-to-all connectivity froze into a specific, sparse pattern, and from that newly ordered lattice, our familiar three-dimensional space spontaneously emerged. The links between nodes can be thought of as being on or off, active or inactive. In the hot early universe, nearly all links were on. As it cooled, most switched off, leaving behind the particular pattern of connections that defines the geometry we move through today. This model provides a breathtakingly concrete picture. The speed of light, the ultimate cosmic speed limit, is not a fundamental constant written into the universe's first line of code. Instead, it emerges from the effective speed at which information can travel across this frozen network, hopping from one connected node to its neighbor. A photon's journey across the cosmos is not a smooth glide through a continuous void, but a relay race across a fixed, underlying graph. In this framework, space itself is a kind of quantum phase of matter, much like ice is a phase of water. The empty vacuum we perceive is not nothingness, but a highly ordered, crystalline state of this fundamental network. This perspective answers a deep question about the birth of our cosmos. Before the crystallization of space, there was no here or there, and therefore no traditional Big Bang singularity. There was only the quantum graph in its hot, disordered state. The beginning of our universe as we know it was not a moment of infinite density, but a moment of cosmic freezing, when the gravity of the quantum network settled into the structured geometry that would become the expanding stage for all that followed. A single electron can be in two places at once, a ghost of possibility. Yet the moment you look, it snaps into a single, definite location. This is the quantum wave function collapsing upon measurement, the shift from a shimmering cloud of potential to a solid point of fact. But this simple description hides a deep and unresolved mystery. What, in the end, actually counts as a measurement? Is it the click of a detector, the act of a human seeing the result? This is the infamous measurement problem, and it strikes at the heart of what we mean by reality. The traditional Copenhagen interpretation draws a sharp line between the quantum system and a classical observer. Something large and definite, like a measuring device or a person, is needed to force the quantum world to make up its mind. Yet this raises a difficult question. If everything is ultimately made of quantum parts, where does this mythical classical world actually begin? An alternative view, the many worlds interpretation, offers a breathtakingly different solution. It suggests the wave function never collapses at all. Instead, at the moment of measurement, the universe itself splits. In one branch, you see the electron here. In another, an identical version of you sees it there. Every possible outcome is realized in its own separate, non-communicating reality. This problem of observation becomes exponentially more puzzling when we apply it to quantum gravity. If the fabric of space-time is itself a quantum object, existing in a superposition of possible geometries, then what could possibly serve as the external observer to measure it? There is no outside to the universe, no larger classical stage on which to stand. One compelling resolution is that a classical space-time emerges through a cosmic version of decoherence. Just as a quantum particle interacting with its environment loses its fuzzy superposition and begins to behave classically, the quantum fluctuations of space-time might settle down into the smooth geometry we know through their interactions with everything contained within the universe. The immense complexity of the cosmos itself acts as its own observer, constantly measuring and stabilizing its own stage. This line of reasoning has led some to venture into even more speculative territory, pondering a possible link between consciousness and the collapse of the wave function. Could the presence of a conscious observer be the ultimate factor that crystallizes reality from the quantum haze? This is a highly controversial and philosophically charged idea, far from the scientific mainstream. While it is likely not the final answer, it serves a profound purpose. It forces us to confront our own role in a universe where the very stage upon which we stand is a probabilistic quantum construct. The measurement problem, therefore, is not just a technical puzzle. It is a fundamental inquiry into the relationship between the world and the mind that seeks to understand it, a mystery that remains as open and vast as the cosmos it describes. The final shape of this cosmic puzzle remains hidden, but its outlines are becoming clearer. The ultimate goal is a theory of everything, a single, elegant framework capable of describing every particle and every force, from the frantic dance of quarks to the majestic curve of a galaxy's path. This is not merely about tidying up the laws of physics. It is about discovering the universe's foundational language, a grammar so deep that both quantum chants and relativistic geometry arise as different dialects. The great debate continues between the sprawling mathematical landscapes of string theory and the granular, discrete geometry of loop quantum gravity. Yet the future may not belong to one alone. A grand synthesis is possible, where these seemingly rival ideas are revealed as different perspectives on a single, deeper truth, a core reality written in the universal language of quantum information and entanglement. This common ground is where the most exciting work now unfolds, searching for the fundamental axioms from which space, time, and matter are all derived. To move from beautiful mathematics to tested truth, we must listen to the universe itself. The next generation of experiments will be our guides. More powerful particle colliders will probe energies closer to the dawn of time. Space-based gravitational wave observatories will feel the faintest ripples in space-time, potentially sensing the quantum jitter of the cosmic fabric. And ever more precise maps of the cosmic microwave background will search for the faint imprint of primordial gravitational waves, the first tremors of the Big Bang. The discovery of a complete theory of quantum gravity will be more than a scientific triumph. It will be a philosophical and technological revolution, fundamentally altering our relationship with reality. It could unlock an understanding of the universe's ultimate fate and open doors to capabilities that sound like science fiction, from engineering the structure of space-time itself to harnessing the power of singularities. The journey is far from over, but the path forward is illuminated by the brilliant, if elusive, quantum threads we have begun to trace. Our most basic intuition that one event must happen before it can cause another begins to dissolve. If time itself is not a fundamental river flowing in one direction, but an emergent property of a deeper quantum network, then the iron law of causality becomes a provisional rule. It is a pattern that holds in our large-scale, classical world, but may not be written into the universe's most basic code. This leads to the startling idea of a block universe, a timeless, four-dimensional tapestry where the past, present, and future all exist simultaneously. From this God's eye view, your birth, your life, and your ultimate fate are all equally real, their events forever stitched into the cosmic fabric. The feeling of a moving present is just that, a feeling, a perspective we have from within the tapestry, unable to see the whole. This radically reshapes what it means for an object to possess properties. An electron does not have a spin in and of itself. Its properties are defined purely by its relationships and interactions with everything else in the quantum network. An object is not a solitary thing, but a knot in a web of connections. So what does it mean to exist in such a world? The very idea of a substance, a fundamental stuff that things are made of, loses its meaning. Reality is not a collection of things, but a vast, dynamic network of relations. There is no stage, only the dance. The separation you feel between yourself and the distant stars is a powerful and persistent illusion, a consequence of the specific pattern of entanglement from which our familiar space has crystallized. While this can feel disorienting, it is also a profoundly unifying vision. It suggests that at the most fundamental level, the cosmos is a single, interconnected whole, and we are not merely inhabitants of this web, but inseparable expressions of its intricate quantum weave. A wormhole is not a shortcut you can simply fly through, and a quantum particle is not a tiny magic charm. The profound ideas emerging from quantum gravity research have sparked a wildfire of imagination in popular culture, but the journey from theoretical possibility to practical application spans a chasm of misunderstanding. Science fiction presents wormholes as convenient galactic highways and entanglement as a form of instant communication. These are powerful narrative devices, but they gloss over the staggering physical realities. The energy required to stabilize a traversable wormhole is beyond any technology we can conceive, likely requiring the mass energy of entire stars manipulated with impossible precision. The spooky connection of entanglement cannot transmit a single bit of information faster than light, a fundamental limit preserved by the very laws physicists are trying to unite. This gap between speculative fiction and hard science is not a failure of imagination, but a challenge for clear communication. The true wonder lies not in fantasy technologies, but in the radical rewriting of reality these theories propose. Understanding that space itself may be woven from quantum threads is a revolution in human thought, far more transformative than any fictional teleporter. The real task is to share this staggering beauty without the distortion of sensationalism, to inspire a young mind not with the promise of a starship, but with the allure of a first principle. The greatest reward of this quest will not be a new gadget, but a fundamental answer to the ancient question of what the world is. Our journey through the quantum threads of reality brings us to a profound shift in perspective. We began with a universe divided, where Einstein's smooth space-time could not reconcile with the frantic quantum world. We have traced the radical idea that this very fabric is not fundamental, but an emergent tapestry woven from countless invisible connections. The ghostly link of entanglement appears to be the needle stitching space together, while black holes act as cosmic looms, revealing how information is not just stored, but is the very thread from which everything is spun. The stage upon which we thought we stood is revealed as a magnificent and dynamic illusion, a pattern that perpetuates itself from a deeper quantum source. As physicist Carlo Rovelli so eloquently reminds us, we are not stuff that abides, but patterns that perpetuate themselves. This grand exploration is far from over. Each question we answer unravels new mysteries, and every thread we pull brings us closer to a unified understanding of the cosmos, a single set of laws describing everything from the birth of a galaxy to the fall of a leaf. I would love to hear which of these ideas resonated most with you. Share your thoughts and questions in the comments below. If this journey into the fundamental nature of reality captivated your curiosity, please subscribe for more deep dives into the universe's greatest mysteries.